Meow. 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 Hi everyone. Is this thing on? Let's check it. Meow. Looking good. Okay, my name is Kitty. Welcome to KittyCoding. And today we are finally going to do what I wanted to do last time, which is that I wanted to show how to reverse a singly linked list. Oh no, I forgot to update my description. There it is, reverse linked list. Okay. So before I jump into, I'm just going to show you the problem description first. So they give us a singly linked list, and the singly linked list, it goes from, it's just a list of nodes where each node points to the next node in the list, like this. 1 points to 2, 2 points to 3, 3 points to 4, 4 points to 5, and 5 points to null. And the goal is that we want these nodes to be pointing to each other in the opposite order, 5, 4, 3, 2, 1, just like that. So they're passing in a list node data structure. In this case, they defined the data structure for us, which is nice of them. It has an integer value in it, and it has a pointer to the next list node. Meow. And they give us some constructors just to make our lives a little easier so we can create new nodes. And the goal is to return a new list where all the nodes are reversed. So I don't know if they intend for us to do this in place, or if they intend for us to create a new list of nodes made of new nodes. I think we can do it either way. One is called the in-place solution, and one is called the out-of-place solution. They're going to have at most 5,000 nodes, so we're not going to have to do like millions of nodes here. And they say the values are between minus 5,000 and 5,000. That doesn't really matter. We're just copying the values anyway. Okay, so next I am going to, you know what, my ears are blocking the chat like a lot. I might just move that chat box a little bit up. Let's see what I can do. Nah, I'll worry about it later. Let me know if my ears are blocking the chat too much. Okay, so, first of all, I'm going to walk through how we do reversing a singly linked list in my iPad. So iPad view. Wow. And I'm going to grab my iPad. You may be surprised to learn that kitties can use iPads, but it is actually factually a fact about cats. Now you know. They can also use pencils. They hold them between their paw beans. It's very, very, very difficult for me, but I do it for you. Meow. Okay, so singly linked list. In a singly linked list, you have nodes. So a node is really like a data structure, and it contains a value, and it contains a pointer to the next node. You know what? These lines are a little bit too thick. I like thick lines, maybe not that thick. There we go. Okay. So we're gonna have 2, 3, and I'm just gonna start with 3 nodes, because that's enough to show the basic idea. That's a terrible 3. There we go. Okay, so this points to null. Or a null pointer in C++, really. Okay, so there's a lot of ways to do this. To reverse it, one of the first ways I want to show you and I want to describe is going to be this interesting technique where we basically just make a little array, and the array is going to have pointers to each node, like this. And they don't talk about this technique a lot when you look up this problem, but it's actually a really flexible technique. It lets you solve a lot of problems like this. And it uses just linear space, which is the same amount of space that the recursive solutions use. So the best solutions for this problem use constant space, but using the same amount of space as a recursive solution, in fact, even less space, because it's actually a compact array and not a whole bunch of stack frames that have additional data on them, we can actually just take these pointers and then use them to build the reverse list. In other words, we're going to take the pointer here and use it to put this node first, and then we're going to take the node here and use it to put the second node in, and then take the node here, use it to put this one. So this is a solution that uses linear space and uses this little auxiliary array, and it's an iterative solution. So I'm going to show you that one first. After I show you that one, let me go back in time here. Tap, 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 tap. I'm going to show you the recursive solution. The recursive solution also uses linear space. It's probably the least efficient solution, but it's still fun. It's actually the most natural solution in some functional programming languages, and the idea there is you have like a head node, which in this case has 1 in it, and it points to just a big cloud. And in this cloud is the rest of the list. The rest of the list. We don't worry about what's in there. It's the rest of the list. And then the idea is if we can take the rest of the list and we can use the same function recursively to reverse the rest of the list, which I'm going to write like this because I'm silly, then all we have to do is take that, point it at our 1 node, point that at null, and we're done. So to make this work properly, it helps if you can keep track of where the final node of the returned list is. So it's good to be able to return that when you're reversing the list. If you're using this recursive solution, otherwise you have to iterate all the way from the beginning to the end in order to add this link afterwards. Okay, so that's the recursive solution. And then I'm going to talk about the constant space solutions, which are the most efficient ones. Mrow. So the most efficient solutions are the ones where instead of creating a new list or instead of using these temporary data structures, we're actually just going to kind of go in and be like, well, if I just take these pointers in the middle and I kind of flip them around, then I can just have 3 pointing to 2, pointing to 1, pointing to null. And now, since I flipped the pointers around, the list is going in the opposite direction, but it's the reverse of the original list. And we didn't have to move anything else. So this is constant space because we don't have to save any very much temporary information in order to do this. But we still got to reverse the list. And it does destroy the original list. So this list, it's gone. It's dead. It's horrible. How could you do this to my list? It was my only list. It's gone. It's a destructive operation. So because it's a destructive operation, that means that the original list is gone, only the reverse list remains. Sometimes that's what you want if you don't care about the original list anymore. Other times you really want to have both of them. Or sometimes the original list is immutable, someone else has a reference to it, they're still using it, you don't want to mess with it. So the solution you use really depends on the situation. Okay, so next. By the way, if you are watching, please feel free to jump in with any questions in the chat. I'm happy to answer questions, and I'm happy to also take suggestions for problems to do in the next KittyCoding. Just let me know. Okay, so I'm gonna switch back to our coding view. We're back in coding land. And I'm gonna put my iPad off to the side. Last time I left the screen on the whole time. It was terrible for my battery. Okay. As you know, cats hate it when you waste battery power. It's very, very bad for kitties. Okay. Next. Here's our code. So first I'm gonna show you that first solution I had in mind. You know what I'm gonna do? I'm gonna do a solution where I build a whole new list and where I just copy the values over. And this solution is in some ways the dumbest solution, but it can generalize to a lot of other problems. So I'm gonna show you. So what we're gonna do is I'm gonna create a vector of ints with all the values. And then we're just going to iterate through this list. Remember, if you want to iterate through a linked list, you have to create a list node that points at the beginning of the list, which is head. And then, until you get to the very end of the list, which is indicated by a null pointer, you're going to do node equals node next. And that will get the next pointer, and we'll jump from one node to the next by following the next pointers over and over again until you've gone to every element of the list. Now, if I just take in this values array and I push back every value that I see, which will be node val, now I've got all of the values from the list inside this values array. And this is a vector, which is a dynamic array, so it will dynamically expand, sometimes called a array list, and it'll dynamically expand to accommodate all these values. And only these values, so it's only storing the integers and nothing else. So once I have all these values, then it's pretty easy to just say, well, I'm just going to go over them backwards with this backwards loop. And I'm going to make some new list nodes. So here's how you construct a new linked list from scratch. So first of all, I have to remember to keep track of where the head is. It's going to be our first node. Let's see, how am I going to do this? So I have to remember where the head node is, and then I have to keep attaching them to the previous node. So you can see we have these constructors, which let us construct a list node with a value and with a next pointer. So I'm going to make I have to allocate these on the heap, because if I just did like list node 5 like this, then this node would be allocated on the stack. And that means as soon as I return, it ceases to exist. It's gone forever. And so we can't do that, because if we return a pointer to a node that's gone, that's been deallocated, then any reference to it will be a dangling pointer. So we can't do this. Instead, we have to say list node equals new. Actually, I'm already using list node up here. So it's going to be a pointer to a list node, but since I already declared pointer to list node up here, I'm just going to say node equals list node. And I'm going to put in it our first value. So we don't know what our first value is yet, but it's going to be in here. So let me think about this. So I have to node equals new list node, and it's going to get values I. And then it has to be linked to our data structure so far. So I'm going to have list node new head. And that's going to be null pointer initially. I'm going to have list node prev node. That's also going to be null pointer initially. And I'm writing these null pointers to be explicit here because I don't believe C++ will automatically initialize pointers to null. By default, they just get whatever's sitting around on the stack, and that would be bad. It could be garbage. So we're going to initialize these to null pointers. And then I'm going to say, if this is the very first node we've made, in other words, if new head is still null pointer, then we're going to set up new head to point to this node. And if there is a previous node, in other words, if prev node is not null pointer, then we can point previous node, its next pointer at the new node. So that will make our new node come after previous node in the list. And then finally, we set prev node equals node, which means the next time we go around this loop, prev node is going to point to the node that we made last time around this loop. So now we've built a list. And some of you might note that I could have just written if prev node here, and I could have just written if not new head here. I'm just being super explicit, and whatever style you prefer is totally okay. Meow. Okay, so I'm going to go ahead and, let's see, meow. I'm going to return new head, and this should do the trick. This is not the most efficient solution, but it is a very flexible solution because once we have all the values saved in these values array, we can take them out in any order we want when we make the new list. So we could do it forwards or backwards or alternating or whatever we want. It's really flexible. Ta-da! I'm passing all my test cases, which is good. So the test cases they give us is 1, 2, 3, 4, 5 to 5, 4, 3, 2, 1, 1, 2 to 2, 1, and empty to empty. This is an important case. We should take a look at my code to see why it does empty to empty correctly. So in this case, value size will be 0. New head will get set to null pointer. This loop doesn't execute at all because value size is 0. And so we get to the end and we return new head, which is null. And that's exactly how you represent an empty list. So that's good. It's also good to think about the case of when it's a list of only one thing in it. So in that case, values will have a size of 1. And the first time through this loop, we will grab that value out, make one new node, it becomes the head. And there is no prev node, so nothing points at it. And because we use this list node constructor that takes only one value, its next pointer is automatically set to null, which is what we want. And then prev node becomes the new node, but it doesn't get used. And then we return the new head, which is the node we made. So we're handling all these 0, 1, and 2 cases correctly. So that's good. I'm going to submit it. And I expect we're going to get a terrible result. What? Really? Okay, I appear to have accidentally beaten 81% of submissions on my first try. Mrow. I'm not quite sure how I did that. Mrow. Well, certainly didn't beat them in terms of memory consumption. I only beat 9% on that because this is a out-of-place algorithm that constructs a new list and not an in-place algorithm. But let's think a little bit about how could this possibly be so fast. You can see it's an ON algorithm. You have to be ON because you can't reverse the list unless you look at every element of the list. So we have to be ON, and so we looked, this is like the best complexity we can get in terms of time complexity. And I think part of the reason it's so fast is because vectors are inherently just a really cache-efficient data structure. Pretty much anywhere you can use a vector, it's going to end up being pretty fast because in a vector, you can just do, all the values are stored in adjacent locations in memory. And that's what caches are good at, because when you load one cache line, you load in all the other values that are next to it in memory. And so they all get loaded into that super fast memory. So this helps us avoid more memory operations and more cache fetches. Fetches. I like fetching, even though I guess dogs like fetching more, but I still like fetching into the cache. When we construct this new list, we are doing a bunch of heap allocations, and those are going to be pretty slow. But if they are small allocations, and if it's an efficient allocator, then it might just grab some pre-allocated small blocks, in which case that's not too bad. But we can definitely, I think, do better. So next, we're going to talk about a slightly different version of this one, where imagine that instead of having integer values in this list, we had some giant data structure here. It was like info, and it was like 4,000 bytes or something. So that would be a really, really big data thing, and that means we don't want to copy this around in order to make our reverse list. So instead of copying it around, we can actually we can try to reverse the list in place and not create a new output list, but also still use vectors in the same way, which means that we're going to have a list of pointers instead. So we're going to call this nodes, and we're going to have nodes in order. So here's how it goes. Instead of pushing back node val, we're going to push back node itself. Dun dun dun! The whole node, a pointer to the node rather. So this vector is going to contain pointers to all of the nodes in order from the beginning to the end. So once we have these, we can do, instead of constructing a new output list like we did here, we're going to reuse the same nodes so we don't have to copy the data values around. We only need to update the pointers. So what we're going to do is we're going to iterate backwards through the nodes. Oops, I needed to make this nodes. There we go. So I'm going to take this node and I'm going to, what was I going to do? I have to set up their pointers in order. Okay. So what I'm going to do is I'm going to say if I is greater than 0, in other words, if we're looking at any element except for the very first element of the list, then we can just set nodes I next is gonna be equal to nodes I minus 1. So we're pointing it at the previous element of the list. And then, if I is equal to 0, then it's at the very first element, which means that the next is gonna be null pointer. And this is it. It's surprisingly simple. Since we have pointers to all the nodes, we can just point it directly at the node that we want to point to based on its index in the list. And then at the end, we will just return nodes, node size, -1, the last one, which is going to be the first element of our new list. And this should be nodes. Okay, I think this will work. Let's find out. Oh no! It didn't like that. Meow! I destroyed the world! Meow! Meow! I appear to have messed up my pointers at some point. So let's take a look at the test case. 1, 2, 3, 4, 5. Okay. So I think what I messed up here is nodes is getting node, which is head. Okay, this part looks okay because it's never going to push anything except each node of the list. And here, nodes I next equals nodes I -1 next. Or wait, no, that was right. What's going on? Let me think about this. Give me 1 second. I feel like this should be correct, but I think I might be missing something important. Let's go ahead and use our debugger to help us out. Debug. And you can see that our nodes points to the first node, the second node, the third node, the fourth node, and the fifth node. It renders each of these as like a little list because it's following the whole linked list. The debugger knows how to do that from that point forward. So, nodes. I'm just going to step through this a little bit, see what's happening. If nodes I next becomes nodes I -1, then it finds a cycle, so it doesn't like that. But let's go ahead and step through this. See if anything unexpected happens. Okay, you can see now the final node is 5, 4, 3, 2, 1, just like we wanted. And then I'm returning nodes, node size -1, which I think is what I want. So is this not correct? No, it produced the right result. Oh, it must have been one of the other test cases that broke. Let's take a look. Oh, of course, this won't work if the list is empty. We can't index into that. So let's think about the empty list case. In that case, this guy will be empty. So I'm just going to make a special case where I say if the list is empty, we return null. Otherwise, I'm actually not going to use the ternary operator because I want to make this a little clearer. Node size is 0. In that case, we return null because we can't get the last element of a list that's empty. Otherwise, we're going to return the last element. Okay. Submit. Okay. I think this will work. And just to refresh what we did here, we made this vector of all the list nodes in order, pointers to each of the nodes, and then we set them up so that each one points at the previous one and the first one points to null. And then we just return the last one in the list, or null pointer if the list is empty. So again, this is still beating like 76%, so it's surprisingly reasonably fast, and it's also doing better on memory, although it's only beating 20% on memory, even though it is, because again, we're using this vector here, and that's not surprising. So this is not a constant space solution yet. So next we're going to talk about the recursive solutions, which I promised I would talk about. So for the recursive solutions surprisingly are actually more inefficient even than this solution. And a lot of people are surprised by that because they think they don't think about the space that's used by local variables in their recursive functions. But when you have a recursive function that calls itself n times, and it has a constant amount of local variables, you end up using linear space, ON space. So it's actually just as much space, linear space, as using this vector approach. And it's actually even more because each stack frame has to keep track of not just the location of the node head pointer, but also where it needs to return when the function is done, and any other local variables that sit on the stack. So it's going to end up actually using 2 or 3 times, maybe 4 times as much memory as this solution, which is surprising because a lot of people don't even think about using a vector. All right, we're going to look at the recursive solution next. Mrow. Okay, so for the recursive solution, I mentioned this earlier. Remember my little cloud? I'm going to show you again. Turn on iPad. Turn on iPad. Okay. Meow. Meow. Okay, here's my iPad. I think my iPad is disconnected. Oh no. Reconnect iPad. Come back to me. Meow. I loved you. Come back to me. Restart. Starting receiver. Okay, we're doing it. Meow. Meow. Sometimes my tools do not work the way I intend them to. Alright, you know what? I don't need to show you that diagram again. I am going to, next time, just leave my iPad on so we don't have this problem. Okay. Like I showed you before, there was a little cloud. That was just the rest of the list, and we reversed the rest of the list, and then we attached the first node in the list at the end of that. So if I want to make this easier, so first I'm going to do this in the simplest way, and then I'm going to show you how we can make it faster by returning the last element in the list in addition to the first element using a helper function. Okay. So we're going to have head. So first of all, if the list is empty, if it's null pointer, we just return null pointer because the reverse of an empty list is also an empty list. If it's not null, that means that we have a head pointer and we have a next pointer. So I'm going to call next the rest of the list, and this might be null, in which case the rest of the list is just the empty list. That's fine. And then I'm going to reverse it. I'm going to say reverse list rest. And now we are going to take this reverse list of the rest of the list after the first element. So this is basically elements 2 through n, where 2 is the second element of the list and n is the last element of the list. Or 2 through last, you could think of it as well. And then we reverse elements 2 through last, and this becomes last through 2. This is kind of Python slice notation, if you're familiar with that. And then we're just going to add the first element, the head element, onto that. So to do that, we are going to go to the end of the rest reverse list, which we have to traverse all the way through the list to find. Such a pain. It's fine though. So we're going to find the end of rest reversed. Keep in mind that rest reversed might be null if it's an empty pointer. Then we're going to say while this is not null, and also its next is not null, because we want to stop before we go off in the null territory. You know what? This will be a little simpler if we treat that as a special case. So I'm going to say if head next is null, in this case there's only one node. It's a one node list, and in a one node list you reverse it, you get the same exact list back. So we just return head. That's it. Otherwise there's at least 2 elements, and that means that this rest is going to be non-null, and this rest reversed also going to be non-null. That makes our lives a lot simpler. So we're going to say node gets rest reversed, and then while we're not at the end of the list, which would be indicated by node next being null pointer, we're gonna traverse through the list. So now, once we get to the end here, this is gonna be last node of rest reversed is gonna be node. So we got it. And once we have that, we can say next equals the first node, which is head. And then head is gonna get null pointer as its next. And that's it. We reversed the rest of the list. We got the last node in the reversed rest of the list. And then we pointed it at our head node. So the first element now comes after the last element of the last rest reversed. And then we point heads next to null because it's now the last element in the whole list. And then the result is just going to be the first element of this rest reversed list, which is, as you remember, this was n through 2. So we took n through 2 and we added it was elements n through 2, and then we added element 1 to it. But element n, which is the last element of the original list, is still the first element of rest reversed. So we can just go ahead and return that now that we've added element 1 onto it. So this should work. We're returning something in every single one of these 3 cases. Let's give it a run. Submit. So you can see this is pretty fast, which is good. It's not good on memory, not good at all on memory. And like I said earlier, you can actually see that if we look at our submissions, this one, which used the vector of pointers, was actually beating 20% on memory. And I think this one was not. I'm not sure why that difference is there. That might be a little random, but 13.38, 13.14, it's not a big difference. So, and you can see this one is also very slow in terms of runtime, and that's because there's just a lot of overhead for making all of these recursive calls. So this is really not an efficient solution, at least in this language. If this were a functional language where recursive calls are heavily optimized, it might do better, but it's still not tail recursion. I'll explain what tail recursion is in a little bit, but this is not tail recursion, and tail recursion is a special kind of recursion that can be optimized and run faster, and this is not tail recursion. And so I'm going to talk a little bit about optimizations here. So first of all, notice that after we return from this reverse list, we had to find the end of reverse list, and we had to do this whole loop to get it. And that's a little silly because this function reverse list, when it's done, it actually knows exactly where the last node of the list is. We didn't have to go and find it, so it could have just told us. So I'm going to show you what I mean by making a helper function. I'm going to take all this out. Whoops, should have taken a little more out. I'm going to have a helper function. I'm going to make it private. I'm going to put it up top here. I'm going to call it reverse list helper. So it's going to return the new head of the list just like before, but also it's going to return the tail of the list using this reference argument. If you haven't seen a reference like this just lets you pass in a pointer, and then when we overwrite tail by doing tail equals blah, it will actually update the original variable. So let me show you. If I do reverse list helper, and then I pass in, and I have some list node tail, and I pass in head tail, then tail will get overridden with blah, and it will actually see it back in this parent calling function. So that's what the reference is for. Okay, so how am I going to get the tail? So first of all, in this case, it's an empty list. Head is null, tail is null. In this case, tail is head because there's only one element. So tail gets head, and we return head as the head of the list. In this case, we're going to use this helper instead of using reverse list. And just like before, this is going to give us elements n through 2, but this time we're going to pass this tail pointer by reference Just to be safe, I'm gonna initialize this to null pointer. You never know. And then, once we're done here, once we're done calling this, tail will point to the last element of rest reversed. So I'm actually gonna call this last rest reversed, just like I did before. And now I don't need to do this loop because I already have it. It's ready to go. And then I just do this like before. So we got to get rid of that whole loop, which was nice. And the question is, where did that loop go? Well, we don't need to do it anymore because here we are actually going to fill in that tail is going to be head, because this is, we know, the last element of the reverse list. And that's it. So, Mrow. I think this is it. And oh yes, we also have to call it from the main function, otherwise it won't get called. So in this case, we don't actually care what tail is because we're not returning tail, but we can just do this. And that's it. So we get tail, we ignore tail, and then we just return the head of the new reverse list, which is already returned by this function. So this is the code. I'm gonna run it. Oh no! Unknown type list. What did I type? Whoops. Meow. Gotta type that correctly. Okay, case 1, 2, 3, you can see it's working. And this should run a little faster than the 23 milliseconds. Let's give it a try. 0? Meow! That's impossible. That's impossible. This is actually impossible. This is a measurement error. Clearly I did not run this in 0 milliseconds. It took a finite amount of time. But it was reasonably fast. And the reason is because we're just changing some pointers around and then returning the updated list. It's an in-place operation. We don't mess with the integers, we don't allocate any new memory, but we are making these recursive calls, which are allocating memory on the stack. Sometimes allocating memory on the stack is more efficient because once you're done with the memory on the stack, you can just decrease the stack pointer and free it, and you don't have to go through an allocator and do all these complicated allocation things. So allocating on the stack can be faster than allocating on the heap, and that's a reason why sometimes it's better than the vector approach. But it's not good for memory, as you can see, only beating 9%. So, what can I do next? So I told you about tail recursion. Tail recursion. And how does tail recursion work? So tail recursion is what happens when you make a recursive call and then immediately return the result of the recursive call. And it is possible to write this using tail recursion. Let me see if I can see the best way to do that. Oh yeah, I see how to do it now. So to do this with tail recursion, we have to make sure that when we recursively call ourselves, instead of like saving the result and doing some more stuff and then returning, we have to make sure that we are just returning this directly. But how is that possible? How is that possible? It is possible. And the way it's possible is that we're actually going to pass the first element, which is head, into this helper function along with the tail reference. So I'm going to add one more parameter, and it's going to be head. So the first parameter is the list that's getting reversed. The second parameter is, let me think for 1 second. It's the thing that I want to get added to the end after I'm done. But is this going to work? So after it reverses it, it can add head, but then, this isn't going to work quite the way. You know what? We're going to make tail recursion a bonus part that I'll talk about later. But for now, this is what you get. So I'm going to save, this is saved in my submissions if I want to go back to it later. But for now, I'm going to do the iterative solution. So there are a number of iterative solutions that I'm going to talk about for this problem. And in some ways they are the simplest solutions, but they can also be a little bit tricky because you have to be sure when you're juggling your values around that you don't mess anything up. And I'm going to show you some ways to help you not mess anything up by using more local variables than one necessarily needs to use, just to make sure you're keeping track of everything carefully. Okay, next, iterative time. For this approach, I am going to, let's see, we're going to take head. Just like before, we're going to point a node at head. And we're going to have two temporary pointers. One is prev, which points to the node before node. And then there's going to be next, which points to the node after node. And if node is null, I'm going to initialize this. I'm going to say if node is null, I'm just going to make this null. Otherwise, I'm going to make it node next. There we go. So the first node, let me put this on a new line. Okay. If the previous node of the first node in the list is always going to be null, so I'm setting this to null. And the next node, it doesn't really exist if the list is empty. You know what? I'm going to save myself from dealing with that case by just saying if head is null, return null. Easy. So now this can't happen. And so I can just do node next. Okay. So now we have a node which starts at the first node in the list. We have a prev node which starts at null, and we have a next node which starts at the second node in the list, which might be null if the list has only one element. And now we're going to iterate through the list. So I'm going to have this little loop. Just going to iterate until I'm done. How will I know when I'm done? I think the easiest way to know when I'm done is because... let me think. I'll get to that in a minute. Let's not worry about it. Okay, now I'm going to point a node. I'm actually going to show you this on my iPad. I'm going to reconnect my iPad. Let's hope it works this time. Starting receiver. I'm just going to restart this whole program. Okay. Starting receiver. There we go. Please work. I'm begging you. Okay. Connect. Connecting. Connecting. There we go. Okay, we're back in business. I'm going to bring it up. iPad scene. Let's go. Up. I need to adjust. Hold on. Meow. Meow. Capturing. Capture window. Capture window. Meow. Oh, I minimized it by mistake. There we go. Meow. iPad is back. iPad is back. I did it. Okay. So I'm gonna go make a new page in my gallery. I'm saving all my notes from the previous streams, as you can see. These might be collector items one day. Meow. And now I'm going to show you how this is gonna work. So, say we have a list. 1, 2, 3, 4, 5. And we have prev, and we have current node, and we have next. So prev is pointing at null. There's kind of a null out here. It's fine. And there's another null off the other end. That's how you can think about it. And node is pointing at this guy, and next is pointing at this guy. Wait. Oh no, it's not showing it. Meow. Okay, sorry about that. Meow. Seems to be not updating. That's weird. Meow. I am getting frustrated with this iPad streaming software. I'm gonna restart it one more time. Almost there. Okay, much better. Like I was saying, here's our list. And here is our prev pointer, node pointer to the current, and next pointer. And what we're gonna do, so initially the pointers go forward like this, and we want them to go backwards. So we're going to take node's next pointer, and we're gonna point it to the previous. In other words, node next gets previous. And whoops, that eraser was too large. That's too small. That's just right. Meow. Okay, so now I pointed node next at previous, and now I have to update all these 3 pointers. So the way I do that is I'm going to update node to point where next is pointing. I'm going to update next to point at the guy after next, which is going to be, here's next.next, which is this guy. So I'm going to say next goes to next.next. This is our new next. That's the first thing we do. Well, okay, that's not the very first thing we do. So this is our new next. Let me clarify this. Okay, I will clarify. Give me 1 second. New next is gonna get next.next. And then node is gonna get where our old next used to be. So our new node is going to be next. Notice this is not the new next. This is the old next, where it was pointing before. And then finally, now that node, the new node is there, previous is going to point where node used to point. So this is our new prev. And it's going to point where node used to point. Again, this is the old node where it used to point, not where the new node points now. So I'm going to point prev here like this. And then once we've done that, they're all pointing in the right place for us to go through the loop again. And we can point node's next pointer to previous, just like before. And then we just keep doing that. And then we update our 3 pointers. And then eventually, once next gets all the way over here to the null, then node will get eventually updated to point to next. And it'll become null. And at that point, there's no more nodes to do, and we'll be totally done. And all these guys will be pointing backwards, and the list will be reversed. And at that point, it will not be node that's pointing to the final head of the list, but it will actually be prev here that's pointing to the final head. And then next is pointing somewhere off into oblivion. It passed the null. So this is the basic idea. And I'm actually literally going to, for my first implementation, going to have these 3 extra variables called new next, new node, new prev. You know what? I might, instead of calling this node, I might call it cur for current, just to make clearer what we're doing for the current node. Okay, I'm gonna put this aside. Go back to the code. So like I said, we're gonna have cur head and prev. And we're going to set prev current next to null, the head of the list, and next. And then the new prev current next will be set to the current node, the old current node, and then the new current node will be the next, and then the new next will be next.next. And if new cur gets to the end of the list, then we return new prev, which points to the final element. And then I just assign them over. So prev becomes new prev, cur becomes new cur, next becomes next, new next. And if this were Python, we could do this with parallel assignment like this. But this is not, but you can do similar things in C++ with standard tie, but we're not going to do that here. So I'm going to go ahead and we can start, just like I said, we can eliminate some of these assignments by rearranging these statements. So we can move the prev equals new prev up here because it's not actually used anywhere in this code block afterwards. So we can move it up, and then we can combine these two statements like this and just get prev equals cur. Then we can assign cur equals next directly for the same reason, because if we move cur up here, then cur is not used anywhere in this block. And so we do use new cur, but we don't use the old cur anywhere in this block. And so we can go ahead and combine these two statements, and we just get cur equals next. And then finally, we move, we can combine these last two statements because there's nothing after next equals new next. And that just becomes next equals next next. So now we've eliminated those three temporary variables. And of course, new cur and new prev don't exist anymore, but they've already been assigned their new values, so we can just use cur and prev. So this is the version without those three temporary variables. And then finally, we can also eliminate the next variable by pulling it into the loop like this. So we're going to compute cur next each time we go around the loop, and it's only going to be used for that one iteration of the loop. And instead of doing next equals next next at the end to keep track of the element after next, we're just going to let it go around the loop and use cur next to get the same value. So because we set cur to next, when we do cur next up here, this will actually be the same thing next next. So we don't have to compute it separately down there. So this works. And like I mentioned, we can't actually do cur next here because we overwrite cur next here. And so we have to save it in this temporary next variable so that we can use it down here. That's why we need that temporary variable. Okay, now I'm caught up to where I was. Mrow! I cannot believe I wasn't watching whether my browser was mirroring on the stream. It's fine. I appreciate your patience. I am going to show you now on my iPad what this looks like when we implement it this way. I'm going to switch to iPad view. Okay. We are going to have these 1, 2, 3, 4, 5. And let's say that prev is pointing here. We're in the middle of the reversal. Cur is pointing here. And next is pointing here. Oh, actually, there is no more next because I made it a temporary variable. So now I'm going to set up, I get into the loop, and then I set up next to point at cur next. So it's pointing here. Then I erase this one and point it. At this point, these arrows won't be like this. They'll actually already be pointing backwards like this. And then I'm going to point the next pointer of cur back at prev. And then, because I saved in next the new value of cur, I can point cur over here. And then after that, I get rid of next. I don't need it anymore. I don't need to update it. And I point prev to where cur used to be. And I actually did that in the opposite order that I showed you in my code. So let me show you that one more time. So if I have prev, and I have cur, and I have next, first I put prev to where cur is, which means I point prev here. Then I can point cur to where next is. Notice that I have to update prev first, otherwise cur will be pointing at next, and then prev will end up pointing at next. That's not what we want. So now cur is pointing to where next is pointing. Now we can throw away next. We don't need it anymore. Not for this iteration of the loop. And that's it. Now our 2 pointers are updated, and the next time we go around the loop, we will create a new next that will point at this new cur.next. So this is the most common solution that you might see for this problem. And this is how it works. And I believe I already submitted this, but I'll submit it again. So you can see it's very fast. It uses very little memory. This is kind of, in a lot of ways, the ideal solution. We can simplify this a little bit by, instead of having this while true loop, because we have this if condition at the end, we can just say while cur is not equal to null pointer, we're going to keep looping. Otherwise, we're going to return prev. So this is the same thing, just rearranged. And then we're going to submit. And that's it. We're done. And this is the iterative solution. So I told you, I promised you that I would show you a tail recursive solution. Tail recursive solution. And the question is, how do we do that? Well, one way you can do it is to look at how we did this iterative solution and try and replicate that with a tail recursive solution. So I'm actually going to go back in time a little bit to when we had our 3 pointers, because I think that version is easier to convert to tail recursion. Let's have a look. So here we have prev, cur, and next. And I'm going to have my recursive version, which I'm going to call helper, just like I did before. And I'm going to pass in prev, cur, and next. So I'm going to have all 3 of these passed in. Let's go ahead and make room for them. So I don't need a separate pointer for head, because head and cur are going to be in the same place. And then I'm going to do next. Okay. And now, now that we have these 3, let me think for a moment. I think I should be able to point cur at prev, just like I did before, just like I did down here. Cur next equals prev. And then, let me see. Okay, and I need this base case. So if cur equals null pointer, in that case, we're going to return prev. And this is just like what I have right here. If cur is null pointer, return prev. Okay, and let me see. And then it is a little tricky that this if was not right at the end. So I'm not sure this is going to quite work, but we'll adjust it after we're done with this. Okay, so cur next equals prev. And then we're going to return reverse list helper. And we're going to pass the new prev node, which is cur, the new next node, which is, so the new prev node is cur, the new cur node is next, and the new next is next. So this is what I would do. This is not quite correct here because next might be null. So if next is null, we have to do something different. I think I'm going to just rewrite this a little bit to detect the case where next is null. If that's the case, then cur is already pointing at the last element of the list. And in that case, I can move this up here. And I can, so this will make sure that cur next is pointed at prev no matter what. And then this will, oh wait a minute, there is one more special case for the empty list, which is if cur equals null pointer, then we're going to return, you know what, I'm just going to handle the empty list right here, like I already am doing in this main function. Then we don't have to worry about empty list. The list will always be non-empty, which means that we'll always get to a point where next is null. We'll set cur next to prev, cur will be non-null, and then next, then we'll return cur, just like this. So when next reaches null, which means that it's gone off the right end, we can go ahead and return current. And this avoids dealing with the case here where next is null and we're dereferencing it. So I think this should work. And this is tail recursive because this return line is actually returning the result of the recursive call directly. And this lets the compiler do an optimization that's called tail recursion elimination optimization, which means that basically instead of making this a function call where it calls this function and then returns the result and then it returns that result, it will instead jump to this function, and then when this function returns, it'll return directly to the function that called us. And this basically means that we don't have to save any of the local variables or any of the arguments in this function. They just get, they all get eliminated, and we just, it's kind of turning recursion into iteration, and it makes it from linear space into constant space. I don't know if the compiler they're using here does that optimization, tail recursion elimination, but if it does, that will get us a constant space solution. And you can see in some ways this is simpler than the iterative solution. You have to think about it a little bit, but we only have this one statement here instead of having those 6 variables and we were moving them all around. So this can be actually simpler, and it can still run in constant space, which is nice. In a functional language, this is how you would write this if you wanted it to be efficient, like if you were writing in Lisp or ML, that kind of thing. Okay, and then here, I'm still keeping that 0 size list case because I don't want to deal with it in my recursive function. And I'm just going to return what I do, previous current head. So you can see in my original iterative code here, previous was null, current was head, and next was cur next, or head next, let's say, since I don't have a cur variable anymore. All right, here we go. This is the tail recursive solution. This should work. I'm gonna make this a little bigger so it all fits on the screen. Okay, run. It ran, submit. As you can see, very fast, very memory efficient, not as fast as the previous submission. And I think that's probably just because this compiler is probably not optimizing the tail recursion, but that's okay. Meow. My tail is very sad about this. Meow. This has been a stream of many errors, but I have shown you how to reverse a singly linked list in every way I can think of. And I am going to, hold on. Meow. So this was my best run, and I'm gonna go ahead and submit a solution here. This was before I actually optimized the while loop to move. Let me look at this solution. So this was the solution where I moved prev outside. So this one should have had the same runtime and memory as the previous one, but the measurements aren't always precise. So sometimes you get a little variation. And so I'm going to submit this one, actually. I like this one the most. And I'm sure there's already many solutions like this. I'm just going to say, you know what? This solution's boring. There's a billion solutions like this out there. I'm going to submit something more interesting. I could submit the tail recursive solution if I wanted. It's a pretty good solution. I like this one. Let's submit the tail recursive solution, because if we have tail recursion elimination, it's constant space, it's linear runtime, it's a pretty good solution, so we're going to submit this one. I think it would be fun to submit one of the vector solutions too, but I'm not going to do that right now. Meow. Tail recursive solution. 01 space with tail recursion elimination. And the intuition here, each recursive call passes in previous node, current node, next node. We update current node to point at previous node. Then recursively call to reverse all the remaining nodes in the list. So that's how it works. Time complexity is O(n), because we're making one call for each node, and each call is doing a constant amount of work. There's no loops here. And space complexity is, like I said, O(1) with tail recursion elimination, O(n) without it. And I'm going to remove these comments because everyone knows about that. All right, there we go. This is the solution. All right, thank you everyone for watching. This has been Reversing a Singly Linked List, and Mrow, I'm very glad that you are with me, and I appreciate your patience. Let me know any questions you have if you see this on YouTube in the comments. I will try to answer them there. It was a lovely time seeing you. Mrow. And now it's time to dance out. Mrow. Let's go. I will put a link, by the way. I forgot to mention. There will be a link to this solution under the video on YouTube if you want to reference it. Okay, that's it for today. Mrow. Wow. Bye-bye, everyone.